Okay, so yesterday we talked a big picture, many things, too many things maybe. Today we come down to smaller things and look practical. I will teach now maybe for 10 minutes, 15 minutes, and then we start working together. If you have a laptop, it's good. No laptop, you have paper and a pen, we're going to work together to solve some problems. Firstly, some simple problems, then we go more complicated to see what we can do. But first, I'll just remind you of some of the ideas from yesterday. So you remember this from yesterday. The idea is we take some problem in the world, we'll translate that problem into logic, and we'll start with a simple logic and move up to stronger logics. Give them to the ATP system. I've got lots of them. They're available. They're free on my web server. You just need a web browser and you can use them all. That will produce a logic solution, which we can then translate back to a solution to our problem in the world. And we looked at the example that Agatha and the Charles and the Mayordomo, and Charles went to jail yesterday. Yeah, thanks to your decision. But now we know that Agatha, we know in English, committed suicide. Right, so we're going, and we looked at this very briefly. This problem, to prove that Agatha killed herself, we can write it down in logic. And this is written in the language of the TPTP. This is in the second logic. This is first order logic. You probably have seen that already. It's somewhere in your mathematics classes. Do they learn logic? Yeah, they learn some logic here, I hope. Yeah, right. Then and we saw these things. And we saw, for an example, this is one formula. It's in first order logic. The name of the formula, nombre, PEL 55.1. It's an axiom. It describes part of the world. Question mark in my language. There exists. It exists. X. X lives in the mansion. And X killed Agatha. So somebody killed Agatha, someone in the mansion. At the bottom, we wanted to prove. This is the conjecture, the theorem, the proof we want to find for this. Agatha killed herself. Okay. All right. But now we want to look at just generally about this language, because on your computer or on your paper, you have to learn how to write this language. It's very simple. It is designed to be simple for you people, and simple for computers. So let's just talk about the language. Here's an example again of a formula. And we see here, it's first order, the name, it's an axiom, it describes the world, exclamation mark, for all. It's the same as, that is this one in logic, for all. Everybody knows that, I guess. For all x and y, if x is a subclass of y, that is equivalent that for all u, if u is a member of x, then u is a member of y. The definition of subset. All right, very simple idea. Let's look at the components. This is the general structure of one of these formulae. It has a language. At the moment, we have 4 languages. Today, we will just use this language, first order logic language. All right. The second thing, the axiom. It's this, the role. It tells us, is it an axiom, part of the world? Is it the conjecture, the thing to prove? Or is it something else, a lemma, an important sub-result? We're not going to do solutions. And here, to write the logic, let's just see, how many do people know first order logic? First order logic, you know it? First order logic, first order logic? Not really. 1, 2, 3. All right, so you guys are going to help everybody write things in logic. But we're going to say things, we'll see, we'll ramp up to this. But we know how to write, you know, Boolean algebra. Boolean algebra, yeah, everybody, Boolean algebra. If you don't know Boolean algebra, no good. Boolean algebra, basic math. So we will start off with Boolean algebra. So we'll have not, or, and, implies, implied, equivalent, and inequivalent, exclusive or, huh? Like that. We'll do that. We also have equality and not equal. That's all we need to write down some ideas. Then, when we've written it out, if you have a laptop, we'll use my computers in Miami to run the problems. If not, you're going to work together to try and write it on paper, and I will type for you, or your friends will type for you. And what we're going to see is we're going to use this system on TPTP. There are three pieces. There's one piece, this one, system before TPTP. That means this is an interface for taking your problem, and before you solve it, you need to check it. When you write a computer program in Java, what's the first thing that Java does? He checks the syntax, do a syntax check, because if the syntax is wrong, nothing works. So, for example, that's one of the basic ideas here. When you write your problem, check the syntax. Then there's this interface. This is the one to solve the problem. All right, you know your problem is well written, good syntax. Now you try and solve it. And we will choose one of the many. We will often use this one, E, very good system. And we will often use this one here, vampire, huh? Because it's a very good one. The others, all good. And finally, when you solve the problem, we saw yesterday the pretty picture of all the lights flashing, the tree, the upside down tree. That's looking at the solution. And there's an interface, this one. This is to deal with the solution, to help you examine the solution and convert it back from a logic solution back to a world solution. So we can do that. We'll see this and we'll practice. So I'm going to go through this process now, and just to show you so you can see the process. For the people who have laptops, you can start at tptp.org. This is the beginning. And inside tptp.org, if you go to the pink one here, this is the tutorial. That's what we're going to work on. So start at tptp.org. And if you don't find it when we get to doing some practice, you can do that. But you can see the URL up here. So if you have a laptop, please try to find that. Just give people a chance to do that. I see laptops flying. I see electrons in the sky. This is all happening. Yeah. Okay, everyone good? Good. I see you translating there. Thank you. All right, so now we're going to start with a very simple example in propositional logic. This is Boolean algebra. Just solving a very simple problem using the TPTP, just to get used to the idea. And so I also wrote this for you in Spanish. This makes life easy now. We can do the Spanish and the English together. So propositions are things that are true or false, like Boolean algebra. In logic, we have not, and, or, implies, and equivalent. All right, it doesn't translate well. And so we saw this problem yesterday, a very simple problem, huh? The axioms that describe the world. If the horse races are fixed or the bookies are crooked, then the tourist trade declines. If the tourist trade declines, then the police are happy. La policía no está contenta. You see, I speak Spanish now. And so this is our axioms, and we want to prove the horse races are not fixed. And if you look at this and you think, yeah, it's true, it's good. But now how can we make a computer do that check for us? So let's just skip that. Let's write it in TPTP format. Where did that other window go? All right. So in this example, we need to write down the axioms and write down the conjecture using the TPTP language. So here we have first order logic. Whoops, sorry. We call the first axiom bad tourism. Here's an axiom. No put axiom, only axiom. And either if the horse races are fixed or the bookies are crooked, and you see we put the brackets, so it's that or that implies the tourist trade declines. Yeah. And that's the same again in Spanish. Notice at the end, close the bracket, dot, punt is the end of each one. Similarly, the next one, happy police is an axiom. If the tourist trade declines, that implies happy police. If you have, we know police are unhappy, not happy police. 1, 2, 3 axioms. Then to prove the conjecture is the horse races are not fixed. That's negation, the squiggle line here, whatever you're at the top of an N. So that's it. So that's the whole problem written in the TPTP logic language. What do we do now? When you write a program, step 1, check the syntax. So how do we check the syntax? I'm going to highlight this. Copy, Control C, over C. And now we go check the syntax. And we'll use, this is the B4 interface. This is to check the syntax and other things. Make it an input formula. And paste. Okay, I'm just watching people. If I'm going quickly, just tell me, wait. If I'm going too fast, but if you're keeping up, that's good. All right. And now I recommend we use the system. Oh, this is checking syntax. For this one, you don't choose anything. The normal action on this interface, when we process the problem, is to check the syntax. So if I go click, and we see no errors. But let's imagine I was silly. I forgot to put that one dot. I made a mistake. I forget the dot. We check the syntax. You see here, line 5, blah, 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 blah. Something is wrong. Tells us there was a mistake. So that was correct. So we put it back. And the syntax is good. And you see. All right. So now we've got it correct. Now we can solve the problem. How do we do the proof? We use the next interface. It's this one over here. This is the solving interface. Again, we can put the problem in here. Paste it in. And we will use E. Okay, select the E prover. You're right. You're right. Okay, just stop me. And then we do run selected systems. Proof found. Yay. It's done. We have a proof. Yes. You want me to show that again? Yeah, sure. Okay. So we're going from, on this page, we choose system on TPTP, You got there? Then, oops, daisy, I put choose input formula. I paste it in. You done that? Okay. Then I'm choosing which of the tools, which ATP system, E 3.25. So just scroll down and click, choose one. You got that? Okay, everybody with that? You guys, these guys, hold on. Yeah. Okay, and then run selected systems. This button here says, let's run it. Okay. All right, and you should get like this. Yeah, looks, yeah, perfect. Okay, good. Everyone's proving theorems. It's fantastic here. We're making progress. Okay, you guys at the back, you're right. You got it. You got it. Yeah, you got it. You got it. We can, as things go, we'll go faster. But this looks like yes. All right. This is no good. Very difficult to understand. Yeah, you cannot understand this. It's crazy. So we go back and choose this, also this button, IDV image. Choose this button as well. This is the one to make the pretty picture. All right. Now we do run selected systems. It will make the proof and draw the pretty picture. Yay, yeah, right. So here's the proof. Now we can understand the proof. And to understand the proof, when everyone has this, you got this? You hear? Yep. You got it. Back row. You got it. Behind you. You got it. Okay. How do we understand this? Now we have to go back a little bit and just do a little more remembering from yesterday. Let's think, not compute now. Watch, think. How do we solve the problem? We want to take the axioms and the conjecture. We did that. We gave it to E 3.25. He produced a proof. Now we want to get the solution. But let's remember, how does the tool work? The normal way the tool works. Tool E 3.2.5. This is E 3.2.5. We give him the axioms, we give him the conjecture. He said yes. But inside E, what does he do? He says, I take the axioms, negation conjecture, proof by contradiction, normal from mathematics. Huh? It's a proof by contradiction. And so what we get out here, this is a proof by contradiction. This is the picture. Here is the conjecture. If you put your mouse on it, you can open up. We see it's the conjecture here. The triangles are the axioms, the upside down triangle. And how do you do proof by conjecture? You put the negation of the conjecture. So we put the house upside down. So that negates the conjecture. And now a little bit of operation takes place. And then we start joining things together. Now you will notice that this is CNF. This is a very simple language for inside computers, inside the ATP. And it's a very simple way of saying things. But here we say this one, number 9 is, well, let's see, the conjecture is not horse races fixed. That's the conjecture. So number 9, the upside down is horse races fixed. And we join horse races fixed, number 9, with number 8. Number 8 says tourist trade declines or not horse races fixed. But that's number 8. Number 9 says horse races are fixed. So what do we know? Tourist trade declines. Because it's just, we have the positive, we know that the horse races are fixed. That's number 9. And so it must be that the tourist trade declines. Number 12 is the tourist trade declines. All right. And then it does another inference. And this bottom one here is the contradiction. It says we have reached the contradiction. Okay, so that you sort of got that roughly. Can you make pretty colors? That's the important thing. So now let's go back to here. We're looking at this. This is how the theorem prover works, E3.2.5. He takes the axioms, he takes the negation of the conjecture, and he finds a contradiction. But what would happen, oops, a daisy, if the axioms have a contradiction? Huh? Then we don't even need this guy if we have a contradiction in the axioms. So when you are using these tools in the industry, you have to make sure your axioms have no contradiction before you begin. Otherwise, if your axioms have a contradiction, you can do any proof because of the way it works. So how can we do that? Let's go back into what we should do. Yeah.
Aquí estamos trabajando con lógicas de segundo
First order. First order.
¿Han hecho para la lógica intuicionista?
No, classical.
No.
This one is not intuitionist. We have it, but this one classical, plain classical.
Okay.
Yeah. Yes, CNN is a very simple first order logic. The inside, we need another class. But the inside of E equals 2.5 and many, they convert from general first order to this very simple first order. It's like an assembly code or bytecode for them. And then they work inside using CNN. Because it only has two operations, or the negation. No and, no implies, no equivalent. So it reduces it to a simple one, then they work more efficiently. And you can have a class, and I can explain in 1 or 2 hours exactly. But it's a good, nice thing. So what am I up to? Do back propositional logic. Oh, so what we should really do when we begin, before we run away here, whoa, let's prove the theorem. Before you prove the theorem, you should take only the axioms. And then you can go. Which interface is it? Here we go. So I'm going to go here, and I'll just remove the conjecture. Go on. So now we have only the axioms in the system. We now want to check if the axioms have a contradiction. Okay, so we can. So step 1, only axioms. Okay, got that in your interface? Step 2, to check the axioms. No E, E set. E set 3.2.0 it has. Looks like I have. That's funny. Okay, and then run. And he says here, satisfiable. Let's get to that. That means no contradiction. Did you get to that okay? If I went too fast, I can repeat. No, you have to use E set. You did, and you get, yeah, no profound, yeah. This is the important line. This line means no contradictions. The axioms have no contradictions, so we're happy. Oh, it will say unsatisfiable. That means you have a contradiction in the axioms. And that means you have to go back and think a bit more about your axioms. Yeah, and try again. So we could make a contradiction here. Let's make a new axiom, just for fun. I'll copy this axiom, and I take out the not. So we see these two axioms have a contradiction. So now we see what he says. He says unsatisfiable. It means there's a contradiction in the axioms. And if you have a contradiction in your axioms, then you need to go back and do some more thinking. Okay. Is everyone happy with every step so far? All right. So, all right, we did this. We drew the pretty picture. So now it's time for you to do your homework. All right. You have to now, here is the problem. I'll put it also in Spanish, so it's easy for everybody. This one. Now it's your turn to write the solution and try. If you have no computer, try writing on paper. How can you write this problem in propositional logic? Yeah, paper. And you? You're not the dean anymore. Everybody must work. Yeah. Okay, 5 minutes to work. If you need help, call me. I'll come help. Sorry. Ah, QUI. This is not translating well. If you are quiet, then you are resting. If you are resting, then you are peaceful and quiet. If you are peaceful, then you are quiet or resting. Therefore, therefore being peaceful does. I think the Spanish translation is wrong. This is wrong. Yeah, yeah. Spanish translation by Google is wrong. Yeah. This is it is as thank you. People saying is fine. Yeah. Yeah, Spanish is wrong. Google doesn't know. This should be it says people is the same as fine. Look at this. This is a mistake. Large language models, hey? Yeah, ChatGPT, wrong. It's true. This is perfect. This is bad large language model. Okay, but you see, you got it? The operators you need. So for and is ampersand. Or is implies. Is that equivalent? Yeah, the bar. Yeah. Yeah, I don't know where it is on the Spanish keyboard. You getting it? I think so. Let's see how the When the talking stops, then we know everyone's somewhere near the end. You got it? No errors? Proof? Next one. You there? Oh, okay. You just wait 1 or 2 more minutes. Yeah. Proof. All right, good. 1 proof. Give that man a banana. Yeah. Good. Now draw the pretty tree. Done? Question? Okay, so I think what we can do, some people are finished, some people are doing it on thick, some people are in the middle. Let's all work together and you can see it, because the first time you're just learning the crazy language. So, so we can take the first one. If you are quiet, then you are resting. Okay. Now, a very nice question came here. What word should you use? Quiet, resting, you are resting. The computer don't care. You can put A, B, C, D. He don't care. Okay. He doesn't know what peaceful is. He doesn't know what resting is. So, but I like to use meaningful things because it's easy for me to understand. So let's go here, starting in the front row. What is your formula here? Yeah. What? Yes. Yeah. So I'm going to use that. So I do. Yeah, like that, huh? And what else? Close bracket dot. Okay, for the syntax. Everyone agree? Simple one, huh? Yeah. Yeah, that's that. Now we're going to do number 2. Not you, we get somebody else. All right, so moving along, let's go. Yes, you volunteer. Yeah, you cannot... It's this sentence, and we're going down to what did you do for? Go away, you think? For this one. Tell me what I must type. Yeah. Implies, yeah. Peaceful. What's that? Paz. I'm doing it in Spanish. Is that right? And yeah. close bracket, dot. Notice here, for people who are doing it on a computer, you have to put these extra brackets there to hold it. There's no precedence of operators. So you need the brackets. All right, then we can do the next one, which is this. So we're going on to, all right, this crew over here, this group. No, the man in the purple shirt. You, number 3. What must I type? Tell me. No idea. Can you tell me, the lady? No? Okay, you've got it. These guys have. If it has, is that okay? No, remember, I must put the bracket here because I mean these two together. So we must have that bracket like that. Okay? All right. And then we want to prove, therefore, the conjecture is peaceful is the same as being quiet. And I know you guys have it, so you got a question? So this is a nice question here, just to help you understand the logic. I put or both, huh? Or both. That's the difference. This or here, vertical bar means A or B or both. And then this one is A or B, but not both. One or the other, exclusive or. And then, so this one I'm saying we can use this one or both. Yeah. So now you have the answer here. Well, okay, well, this is why, sorry, let me go back. That's why I use vertical there. Or both. And this one is tranquilo. Oh, it should be pause, shouldn't it? Right? Yeah, okay. Everyone agrees. Very good. So does everyone understand that? That's happy. You get it, guys in the back? Just making sure. So what is your first step when you've got this done? Step number 1 is to check the syntax. So we can take all this, take a copy. We're going to check syntax. Control C. We go to this guy. I've got it here. It's, let me open this up again. It's the interface before you do proving, you check syntax. So I put it all in here and we can just process it. No errors. So everybody check syntax. You got it. You got syntax checked. Yes. Good, 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 good. Okay. Step number 2, before proving if we are good software engineers, we check the axioms are satisfiable. So we take only the axioms, copy, and we go to the interface system on TPTP. I'll put them in here. And remember to check the axioms, we use ESAT to check your axioms. So it's the interface, this one. System on TSTP. No, not that one. Sorry, this one. System on TPTP. We use that interface and ESAT to check that the axioms are consistent. Voila. Satisfiable. Okay. Did I do that? I can redo it if it's too fast. Everybody got it. Go to axioms are satisfiable. You guys get it at the back? Or too quick? Yeah, you got it. They got it. Yeah, we're getting there. And when you've done that, we can now do the proof. We take everything, put it in here. This is system on TPTP interface, system on TPTP interface. We now do the proof. To prove, we use not ESAT, we use E. Proof found. Hey, you guys got it? You guys getting it? Yes, you guys? Not there. We're going to come around and make sure everyone gets it. I'll come around and help everybody before we take a break. And for the people who got it so far, you can draw the pretty picture, IDV, and there's your pretty proof. So now let's take 5 minutes. If you got it correctly, you guys got it? Help them. And who did not also needs help? You guys okay? You good? I'm going to go help at the back. Everybody else can relax a little bit. Victory. All right, we got it done. And most people got it completely, and some people have left because it's not interesting. What I'd like to do now, and you could see that this is Boolean algebra, huh? Very simple, but you have to correct your spelling. Lots of spelling mistakes. Paceful, peaceful. Yeah, you put every time the spelling because the system doesn't check. This is no IntelliJ. You are responsible. When we go on to 2 more logics, then the logic is strong, then it will check your spelling. But right now, no checking. Another point that somebody just made over here, this gentleman, is that the names of the formulas must be small letters, okay, and underscore. Big letters is for variables, like in programming. Small letters for functions, methods, and things. So we're going to we haven't used variables here, but now we're going to go to the full first order logic where we have variables. Now we have much more power. Here we can say very simple things. But if we want to make a lot of money to buy a barco grande, then we need to have a stronger logic. So let's go back into this story here. And we go to full first order logic. So this logic is much stronger. You can say many more things. It's more powerful. Oh, I see you're charging there. So we're going to see things. There's new parts of the language. But mainly the important things is we're going to have constants and functions and variables and quantifiers. Maybe you have seen this, meaning all things. And you've seen this one, there exists some things. All right, and I don't know if that translates well. So here's an example to show it. All right, just to see the idea. The USA is a country. All right. The capital of every country, I can put it up in Spanish as well. Let's do it. Hold on, I'll put it up in Spanish as well. Sorry, give me a moment. I've got to change it from English to Spanish. Go. Aha. Okay, now we're in Powerland here. So we can see it in both languages simultaneously. Okay, so here's what I want to describe. The USA is a country. The capital of every country is a beautiful big city. Yes, Bogota, beautiful big city. There is some city that is the capital of the USA. Capital of USA is Washington. Capital of Colombia, Bogota. Right? Yeah, that's great. Yeah. Every big city has crime. We know this. Yeah. A big city is still a city. We want to prove there is some city that is beautiful but has crime. All right. So this is a little more complicated story. And so here we could write it in logic. This is the old logic way. If you read a book on logic, here we're saying country, USA. We are saying that USA has the property of being a country. Now we're saying for all C, we notice that the C is a variable. Variables, big letters. Huh? So for every C, if C is a country, that implies the capital of C is a big city, and the capital of C is beautiful. This is in the logic. I just want you to see, because you might be familiar, there exists some C such that C is a city and C is equal to the capital of USA. USA has a capital. So let's now skip on and see how we write that in TPTP format. Again, we're using the FOF, first order logic now, but now we have all of first order logic. The name, USA, the axiom, USA is a country. All right, so that's normal, but a little more than Boolean algebra. All right. The name, country, big city is an axiom. Now we say this is for all. Exclamation is for all in my language. We must put the variable in square brackets, colon. If it is a country, I put brackets here to just capture the whole thing. If it is a country, that implies the capital of C, capital of is a function. You take country and it returns you a city. And we say the capital of C is a big city. And the capital of C is beautiful. Let's just note the brackets here. That is bracketed to there. That's necessary because of the and. And then also, we are bracketed from here to there. That is necessary so that this for all C has to apply to everything here. So we need to put brackets so that for all applies to the whole everything. Let's look for exist. There exists a C. C is a city, and C is equal to the capital of USA. For every city, if it is a big city, that implies it has crime. A big city, for all C, if it is a big city, then it is a city. That's okay. We want to prove the conjecture. There is some C that is a city, it is beautiful, and it has crime. So now, if I scroll that into the Spanish version, just to look over it again, you can see, I hope this translation is good, because I'm just trusting it. I think you can see, but let's look at the extra features we have now. This thing, like place, city, big city, that is a predicate. It tells you if something is true or false. Like in propositional logic, it's just true or false. We are saying it is true or false that the capital of the C is a big city. Capital of is a function, just like in programming, but we don't ever evaluate the function. We just pretend we can evaluate it. Variables, big letters. And here, like USA, it's a constant, or for people who are mathematicians, a function with no arguments. So a function of no arguments is a constant in mathematics. All right, so we can play the same game here now that we did before. First thing, grab all of this and go in to here and check the syntax. All right. And I'll do some mistakes so you can see the kind of problems you're going to face. So this is perfect now, no errors. But let's make something strange now. Let's say instead of C here, I put D, just typing mistake. Okay? What happens? We will see the error now. And it tells us somewhere it's at line 5. So there's more ways to make mistakes now. And so when you're typing your examples, your syntax check, it is probably you will have errors. If you need help, call me, I'm going to come along. And you're going to get right to using this. But it's the same process, but with a more powerful language. And so, are we going? How much time do I have? 2 hours? What time? 6 o'clock is too much? Yeah, it might be too much. Brain gets tired. But let's try. We try for at least, we try at least for 30 minutes, and then maybe we go home and have something. So here is the challenge for you. The challenge problem. Go away. You can see that? Right. Or if you want it in English, I'll have it in English at the top. Go! Attack! First, go! Now you have to do this one. I am learning so much Spanish. This is good for me. Something like that, I think. Have you finished? Okay. Saying for all C, I'm writing in my language, okay? You say, then good looking C implies, you have that, correct? Yeah. Now you want to say one parent or the other. Whoop. Let me write it P. Oh, this is okay, so this is Carlos. This is kind of what you were asking as well. What you need for this is you need a predicate called parent because you have two parents. Everyone has two, right? Normal. So you can't use a function because a function returns only one thing. So you have to use it. So this is saying that P is a parent of C. It is true that P is a parent of C. So here we're saying for all people, if C is good looking, then for all their parents, there's only two, that was what you wanted to say. For all their parents, for all P, if P is a parent of C, then the parent is good looking. Or is it say one parent? Is good look, yeah. Oh, it's one of their parents. Ah. So in fact, we can use that there exists one parent, one person who is a parent and good looking. So you don't need a set there, but you can play with that sort of idea. Oh, so then, no, this is not implies. Must be and. Yeah. Yeah, this is exists. There exists P. There is some P who is a parent of C and is good looking. Exclamation is for all. Yeah, this is true for all people. If it is good looking, then there is another person who is the parent of the C, and that person P is good looking. Means and one there is some parent who is good looking. Logic, eh? Because it could be your mother or your father. So it just exists one. It is then this one. There exists one of their someone. So we say this is true for anybody. True for you, true for me. So it's for everybody. Professor Taylor. No. Okay, here's what I suggest you do. Let me do a couple of them with you so you start to see what's happening and get some ideas. Then we'll talk because I think yeah. You can do it. And then tomorrow, Then we will. Yeah, okay. Oh, yeah, I want to just show you this because this is something you need to understand. The oldest sibling, it's your oldest brother, your oldest sister, huh? You have only one oldest. And if it's only one, then you can use a function. So you see how I've written here, maybe this is bad Spanish, but you get the idea. It says, this is for all people, me, you, everyone. If the oldest sibling is good looking, and this is just one thing, so we can use a function. We don't have to do like parents. For parents, you have two padres. You need to use relation like this, but if it's one, we use a function, then we can put it inside. So it says, if the oldest sibling is good looking, then the person is good looking. So there's a difference between this and this. One is a predicate, true or false. One is identify an object. See, this is a true false. This is something. It's a person. It's my oldest sister. So we use a different type of way. It's more, whenever you can use a function, it is better because E325 is very happy. He likes functions. He goes quicker. Right, so the plan tomorrow is at 4 p.m. We will meet here, but then Professor Fabian will find a room. So if you are tired now, I think it's the time to stop. I will stay until the last person if people want to work more. But tonight you can work more. Tomorrow we revise this. We do one more logic. Then Thursday, Friday, maybe we do some theory. Okay, but I can help if you need help now.
Universidad Nacional de Colombia, proyecto cultural, científico y colectivo de Nación.